Hi everyone, and welcome back to my flight mechanics class. Today will be our last lecture on longitudinal static stability, and we're going to cover the effect of thrust on the overall pitching moment, as well as what the total pitching moment should be in trim. The first thing that I'll say is that the effect of thrust on the pitching moment may differ from aircraft to aircraft, as the design is not always going to be the same. However, in this book, the thrust vector is depicted as being above the waterline of the aircraft, or the x-body axis, and therefore has a negative contribution, or a nose-down contribution. That nose-down contribution is captured by the minus sign in front of t dt in this equation. So now that we have our aerodynamic pitching moment and the thrust pitching moment figured out, we can now establish an equation for our total pitching moment, and because our aircraft needs to be in equilibrium while in trim, the pitching moment is going to be equal to 0. So there are many things to say about that equation. First, you'll recognize the contribution of a lift of a main wing and of a lift of a tail to the overall pitching moment, and this is what we had derived in our previous lecture. Those rely yet again on a small angle assumption, hence the cosine terms being absent. Then the most important takeaway from this equation is that the center of gravity location is the biggest contributor to longitudinal static stability or instability. So let's dive a little deeper in this equation. We know that for a standard wing, MAC is going to be negative. We also know that the lift of a main wing is going to be positive. We also know that XAC of the tail minus XCG, or the moment arm of the tail's aerodynamic center with respect to the CG, is going to be positive for a standard aircraft with an aft tail. And the last assumption that we can make is that t dt is small. So the only parameters that we have left are xcg minus xac of a wing and the lift of a tail. And actually, it is xcg minus xac which will determine what the lift of the tail should be for that equality to stand. So really, it's the sign of xcg minus xac, or the CG location with respect to the aerodynamic center of the aircraft, that will determine what the lift of a tail should be for trim to exist. So essentially, if you have a stable configuration, and that is the CG is in front of the aerodynamic center, XCG minus XAC of the wing is going to be negative. And in that case, the lift of a tail is going to be negative as well. And that is because it has to counteract the nose-down moment created by the positioning of the center of gravity. If you have an unstable configuration, then XCG minus XAC of a wing is going to be positive. And that is because the CG is going to be behind the aerodynamic center. In that case, the lift of a tail is going to be either positive or negative, depending on how negative MAC is going to be. So the next step is to explore the pitching moment coefficient. So we had already derived that in the previous lecture, and we know that the overall pitching moment is going to be equal to 0 in trim. So that means that Cm0 plus Cm alpha alpha plus Cm delta E times delta E plus Cm IH times IH is going to be equal to 0. But what else can we say about these subcoefficients for a stable aircraft? Well, we know that Cm alpha is going to need to be negative. And the reason for that is because that will enable the aircraft to produce a restoring moment whenever there's going to be disturbance in the angle of attack. The next requirement is that Cm0 plus Cm IH is going to be positive. Why is that? Well, because we want the aircraft to be trimmed at a positive angle of attack. And as you can see from the graph, if Cm0 plus Cm IH were to be negative, then the x-intercept would be negative as well. And that would not be acceptable in the real world. So the last parameter is delta E. Delta E is used to modulate the steady state angle of attack. So as you can see, the slope of a curve, which is Cm alpha, is not changed. So it does not change the stability properties of the aircraft. It simply is used to modulate the steady state angle of attack in trim. All right, so that's it for today. Next time we're going to explore the lateral directional static stability, and then we'll finally explore the dynamic stability of an aircraft. Thank you very much. See you next time.